All right, so welcome to Math 150. Whoops, I'm one page behind. Math 150. This is lecture 5, sequences and series. We've already started talking about sequences and series. We're going to do it, more formally now. And I know you've all been missing the ability to hand in written homework. So thank you for waiting. And that will now start on Wednesday. You'll be able to hand in written homework. Starting on Friday, I will be able to hand back graded homework. So, again, TAs and I and the, Math Science Resource Center are always available to talk about things. As much as possible, when I am going to be, stating standard results, I will be using the language from the text just for consistency. You've got to be a little bit careful. Any potential physics majors here, astrophysics, they use different notation than mathematicians do for certain coordinate systems. And you just have to be careful of which one you're using. I learned my coordinate systems from the physicists before, from the mathematicians, so I always have to pause when I'm teaching multivariable calculus. It's not that this is a very difficult concept and I'm being very reflective. It's that I am resisting my instincts because I first learned how to speak about this from the physicists, and they've switched the angles from the mathematicians. Whatever you do first, it's very easy to just get caught doing that. So always watch and see what notation the book is using, because different people use different notations. One of the things I truly despise my wife for doing is introducing me to one of her cousins as Danny. He's Dan. He hasn't been Danny since he was a little kid, but she's older than him. She still calls him Danny. And because that's how she introduced him to me, I'm still fighting with that. So really watch what notation you're using. Different places use different ones. All right. So a sequence is basically a series of terms. When I talk about the integers, well, the integers is everything. It's the positives, it's the negatives, it's the zeros. When I talk about the natural numbers, do the natural numbers include 0 or not? Sometimes people talk about the whole numbers and what's the difference between a whole number and a natural number. For the most part, it's convenient to allow 0, except sometimes when it's not. So just be aware that sometimes we start things at 0, sometimes we start things at 1. It doesn't really matter. If we're trying to decide what's going on in the limit, I can throw away finitely many terms and it's not going to affect what happens in the limit. I want to know, where does it end up? Well, a couple of fluctuations in the beginning, not a big deal. So for sequences, we might start counting at 0, we might start counting at 1. Sometimes one starting point is more convenient than the other, not a big deal. Okay, and again, this stuff is directly in the book. I'm just putting this here in the slides to make it very easy for you to have things accessible. All right, the limit of a sequence is the number that it converges to if it converges to a number. You can decide whether or not if something is going to infinity, is that converging to infinity or is it diverging? It doesn't really matter. As long as you are consistent, as long as everybody uses the same language, it doesn't really matter what you want. So, hello? Hello? Okay. Yep, nope, that's fine. That's why I'm keeping my cell phone on so that people who are stuck in. All right. Yep. All right, so I was correct to keep the phone on so that I would be able to hear. So it was not flashing that somebody was trying to get in. Interesting. Okay. So again, as long as we all agree, it doesn't really matter. You can use language such as it's converging to infinity. You can use language it's diverging to infinity. As long as you're clear so we know what you're talking about. Who are my potential economists here? Anybody? Okay. So if you're in Zoom land, please hit mute unless you're talking. So price, quantity, which is vertical axis, which is horizontal? Prices. Does price have to be vertical? Would economics fail if we switched? I'm sorry, they wouldn't be happy. Well, I mean, economists happy to be. So, would economics fail if we switched which was the vertical and which was the horizontal axis? Do we have to? But if you use the opposite notation as everyone else, you're going to make it confusing. So when people glance down, it's going to be hard to follow. Notation matters. And so again, if you say something clearly, diverges to infinity, okay, that's quite clear what's going on. It's heading to infinity. If I have the sequence, n times -1 to the n, the terms are getting larger and larger in absolute value, but they're alternating between sign. So half the terms are going to positive infinity, half the terms are going to negative infinity. That sequence is definitely diverging. It's not getting closer and closer to just one of the infinities. We say it converges to a limit L. If as n gets larger and larger and larger, it gets essentially as close as we want. So this is the formal language. We're not going to do too much with this, but if you continue to real analysis, this is what you would do. So for any epsilon, so that's a tolerance. I want to be within 1/10, 1,000th, 1 billionth, 1 trillionth, 1 googolplex, 1 over googolplex. I want to be a certain threshold. I want to be no more than a certain amount away. All right, will you tell me how close you want to be? And I tell you that as long as you look at indices that are larger than m, you will be at least that close. That's what it means to converge, that you give me any window, no matter how small it is, and eventually every term from some point onward is within that window. Can a sequence have two different limits? Could you converge to L1 and L2? What do you think? No, because eventually I've got to be very close. And so if all the terms, are really close to one, they can't be close to another. So limit is unique. Right? You're not going to have two limits. It may not have a limit, but if there is a limit, it's unique because all I have to do is choose my tolerance to be less than, say, 1/10 of the distance between them. And if it's less than 1/10 of the distance between them, I can't be close to both L1 and L2. So if a limit exists, then the limit is unique. So we'll write L for the limit. Did I repeat the page? Or am I repeating the page? It's a really important page. All right, so limit laws for sequences. These are basically the no-shit laws, okay? Assume AN goes to L, assume BN goes to M, then the limit of the sum or difference is the sum or difference of the limits. The limit of the product is the product of the limits. The limit of the quotient is the quotient of the limits. And if I multiply all the terms by C, then the limit is multiplied by C. So you have to be a little bit careful as to what does it mean when we say they're convergent sequences. This means L and M are finite. Whenever there's an infinity in mathematics, you have to be careful. So we talked about last week that if both AN and BN are going to infinities, then maybe infinity over infinity, I can make that whatever I want, depending on how they're going to infinity. Same with infinity minus infinity. What are the things we must avoid? What are the expressions we are not allowed to look at? 0 over 0, that's a no-no. Infinity times 0. Infinity over infinity, one more. Infinity minus infinity. These are the things we have to avoid. These results are actually true if one, but not both of the limits are infinity. If AN is going to infinity and BN is going to something finite, the sum is going to infinity. The only danger is when both of them are infinities. So these are the standard limit laws. And from these limit laws, we get a lot of the results for derivatives. This is how we proved these differentiation laws. And we actually did a proof of the product rule after sniffing it out experimentally. By looking at some simple functions where we could do derivatives, we then saw how to prove the derivative of a product is f prime g plus fg prime by adding 0 in a clever way, and then writing the limit of a sum was the sum of the limits, the limit of a product was the product of the limits. So we crucially use these limit laws to prove that. All right, next is the squeeze theorem for sequences. Imagine AN, BN, and CN are sequences. AN lives between BN and CN, and BN and CN go to L. So the way I might want to view this is here is CN. Here is BN. And here's AN doing something between Bn and Cn? Well, if Bn and Cn are both going to L and An lives between them, it has no choice, but it has to go to L. This is multivariable calculus for people who are probably not going to become professional mathematicians. If you want, I could absolutely spend a day carefully going through all the details of this. Or we can just look at my modern art scribble. I think the modern, and it's in like 4 colors, right? That's the advantage of using this over the chalkboard. So if this is enough level of detail for you, this can be made rigorous. We can have all of our different tolerances and whatnot, and we can show that An gets arbitrarily close to L no matter what threshold you give me. I just want you to know this can be made rigorous. My feeling is that this is more than enough detail for what's going on. This is a pretty reasonable result. All right, the next result, if f is continuous and the limit of An equals L, then f at An is equal to f of L. As we take the limit as n goes to infinity. Essentially, this is what it means for a function to be continuous. If An is approaching L, if we look at, here is L, and here's my sequence of points, getting closer and closer to L. When I'm trying to look at what the function is, because the function is continuous, as I get closer and closer, all of these points, f of An has to get closer and closer to L. That's what it means for a function to be continuous. So continuous, if the limit as x goes to L of f of x equals f of L. That's what it means for a function to be continuous at L. Not only does the limit exist, but it equals the value of the function at L. Okay, most of the functions we look at are continuous at most points. Can somebody give me an example of a continuous function? Continuous function. X squared, another continuous function. X, 1, 0, x cubed. Any polynomial is going to be continuous. Exponential, cosine and sine. Can somebody give me a non-continuous function? 1 over x, that's going to blow up when x equals 0. 1 over x squared blows up. 1 over x squared plus 1 does not blow up. Okay, so there's lots of functions that are continuous. Can somebody give me an example of a differentiable function? So example of a function that you can take the derivative of. X squared. Similar to x squared is the function absolute value of x. That's differentiable at every point but one point. What's the one point it's not differentiable at? Whereas the 1 point x squared is not differentiable. It's 0, and it should be 0. It's the only point where something special is happening. If you go to positive x, then the function looks like x, which is differentiable. If you go to negative x, it looks like the function negative x, which is differentiable. Something happens at 0. There is a strange result that in some sense, almost every continuous function is differentiable nowhere. Or at least, yeah, I'll leave it like that. That's strange. When you think of functions, okay, well, maybe I have something like the absolute value of x, which is continuous, but not differentiable at one point. It turns out that there's a way to talk about the size of functions. Just like we have the integers and the rationals and the reals, and there's a lot more reals than integers and rationals, there's a lot more continuous functions that are nowhere differentiable than continuous functions that are differentiable. Fortunately, the continuous functions that are differentiable are a wide class of functions, and we can use them to model a lot of things in real world. Why are you taking this class? Well, I took math before, so by induction, I keep taking math. So I take another math class. Hopefully, the reason you're taking this class is you want to learn skills that you can use to do things. Maybe you want to model something in economics and physics, maybe something in psychology. And so we want to find functions that will describe the world, and we want to do things with them. Well, it doesn't have to be a perfect fit. I want something that's going to give me a reasonable job modeling. And so these simple functions that we can integrate, that we can differentiate, we can do a lot of modeling with them. And that's why we're doing all of this. And we'll see applications of this later in the semester. All right, so continuing, bounded sequence. So a sequence is bounded from above if, surprise, surprise, there's some number such that everything is less than or equal to that number. It's bounded from below if there's some number such that every term is greater than or equal to that. So one way to look at this is they're using capital M and lowercase m. I would maybe use, there's so many different things you can use. So here is m, here is little m, and then if I look at my sequence, it lives between them. So as long as it lives between them, it's bounded. Most things that we look at are bounded, right? The amount of money someone has is bounded. The amount of objects someone has is bounded. The amount of time we have in this class is bounded. Maybe I'm using too much time saying that things are bounded. There are things that are not bounded. But for many problems we're doing in the natural world, we can effectively say things are bounded. Okay, so a sequence is bounded if it's bounded from above and below. If it's not bounded, in a shortcut, we call it unbounded. You could also say not bounded if you would prefer. That's absolutely fine. It makes things technically easier if we have bounded sequences. There are certain results that are true if we have things that are bounded. Why? Because then we know we avoid infinities. This is the difference between necessary and sufficient. A lot of times it makes work a lot easier if we deal with things that are bounded because we know there's no infinities at play. It doesn't mean that an analog is going to have to fail if it's unbounded. It just means it might because there's an infinity at play. And we'll see some examples later of how things can go along. So the next is the bounded monotonic sequences converge theorem. An interesting one. If you have a sequence AN that's increasing and it's less than or equal to M, then it converges. And the limit is less than or equal to M. And similarly, if it's decreasing and bounded from below. One of my professors at Yale, Peter Jones, was phenomenal at giving great life advice of doing mathematics. And one of the things he told us is remove a condition whenever you see a theorem. If you remove a condition, either the theorem is false or usually the proof is much harder. So let's imagine we remove the fact that it's increasing. So let's say the sequence AN is bounded from above, but not increasing. Does it have to, what do you think? Do you think it has to converge? What do you guess? You have to guess right now, quickly. Somebody yell out an answer. No. I'm saying over there in my assumption that it's increasing. So either that assumption is important or it makes the proof easier. So consider the sequence, AN is -1 to the n. It doesn't converge. So again, the general advice is if you're trying to understand a theorem, the best way you understand a theorem is you basically remove a condition and see what goes on. These conditions are there for a reason. They're eliminating cases. One of the things I found over the years that students have tremendous resistance to doing is just try something. How many of you are old enough to remember when new movies came out? And by new movies, I mean something that's not a sequel. The first movie, we've got Indiana Jones 5 coming out. I think Frozen 3 is Utopia 2. They were originally movies that just were standalones. I think Toy Story 5 is now in the works. So there's going to be Zootopia 2. I actually liked the first Zootopia, and one of their songs, actually, what's the most famous song from Zootopia? Cultural extra credit for today. Try anything. This is something that people have a tremendous resistance to doing. Try something. It's okay if it doesn't work. I want to see what happens if I take a sequence that's not increasing. Try something. Try a couple of sequences. What's the simplest thing you can think of? Well, for me, alternating, +1, -1, +1. And that's already enough to find a counterexample. Don't be afraid to just try something, and if it doesn't work, set the paper aside and try something else. So why is this true? This is basically a result from analysis. And so the proof is something like the following. So imagine here's M, and here are my sequence points. Maybe here's A1, A2, A3, A4. These things are all moving up like this, and they never get past here. This is a little bit technical to prove. I don't really want to go into all the details, but we know that the amount that each term is, we never get above M. So, if this is where A1 is, this is A2, this is A3, this is A, I can look at how much more they're all moving. And the amounts that I'm increasing has to be tending to 0. Clearly, since every term is less than M, there's no way AN can converge to something above M because each term is less than or equal to M. And so I claim that there has to be some number that it's getting closer and closer and closer to. If there is some number such that I'm never within an epsilon window of it, then just decrease what I think the limit is and keep moving it down, keep moving it down, keep moving it down. All right. This is a very rough proof. This is just, hopefully, it seems to make sense. If I'm increasing and I'm bounded by this, I can't just keep going on forever. There's no way I'm ever going down. I'm only going in one direction. My steps have to be getting smaller. Eventually, all steps have to be less than 1/1,000,000. Because if I had infinitely many steps that were more than 1/1,000,000, I'd get arbitrarily large. So I can't have infinitely many steps larger than 1/1,000,000. What about 1/quadrillion? Again, I can't have infinitely many of those. So eventually, all my step sizes are getting smaller and smaller and smaller, and I know I never get above M. Okay. So convergence of an infinite series. An infinite series converges to the sum S if the sequence of its partial sums converge. So we talked a little bit about this with the geometric series. We talked about for the geometric series, if you sum all the way up from 1 to x to the n, you got 1 minus x to the n over 1 minus x. These were the partial sums. And then we said, well, what happens as n goes to infinity? Well, as long as x is less than 1, x to the n goes to 0, and it converges. All right, and so in this case, we'll write that S equals the sum of, and goes from k to infinity. Okay, so we're starting the sum at k. What do you think common values of k might be? Any thoughts? Yes. 1 and 0. Those are the most likely ones. Is that we'll probably start at 1 or 0. Okay. And so I just erased the vertical line after in. That was because when I was highlighting the text and clicking it, I didn't notice that my cursor was actually after the word I. Okay, so for the geometric series, we would have, Sn would be 1 plus x squared all the way up to x to the n. And we showed it was 1 minus x to the n plus 1 over 1 minus x, which we can write in a very nice way as 1 over 1 minus x to the n plus 1 over 1 minus x. And the limit as n goes to infinity of Sn will just be 1 over 1 minus x. So this is a really nice example of a sequence with partial sums that we have a closed form expression for, and we can identify what the limit is if the absolute value of x is less than 1. Okay, so if we know what S is, and if we can do a lot of analysis, we can then say, okay, well, you've given me an S. I'll now try to find, you give me a threshold, 1/1,000,000,000, 1/1,000,000,000,000, 1/quadrillion. I'll then try to find an index such that from all values that large or larger, the partial sums are within that tolerance. And then you give me a smaller tolerance and I do it again, and then you give me a smaller tolerance and I do this again. No one wants to do this, right? You don't want to do this infinitely often for each tolerance. You don't want to have to keep finding how far down do I have to go. So one possibility when you're trying to show that things converge is you have to show from some point onward, you're within that tolerance of the proposed limit. Well, how far you go is going to depend on the tolerance. Typically, the smaller the tolerance is, the further down you have to go to be within that. So one way to do it is to say, okay, I know this is my error over here. If I want to be within 1/1,000,000,000, I figure out what x has to be so that I'm within 1/1,000,000,000. If I want to be 1/1,000,000,000,000, I figure what that is. Or more generally, I want to be within epsilon, so I solve for n as a function of x and epsilon and say, you give me any epsilon, and here's the value of n I take, and I'll win. And if I do something like that, I only have to do one calculation, and now I have a function. You give me a tolerance, I tell you how far I have to go. That's one way to solve problems like this. It's not pleasant. Another way is to develop tests for when does a series converge. And we have a whole slew of tests that we're going to learn. This is similar to the rules of differentiation. So I think I gave you in the past x to the 24601. I could give you x to the 1701. All right, what's the root of x to the 1701? Excellent. And so you've probably never differentiated that, even though 1701 is a wonderful number. You learned a rule for the derivative of x to the n, and then you just plugged it in. We're going to do the same thing here. We're going to learn some rules for finding derivatives. If I give you a quadratic and ask you to factor it and say your entire grade for this class will depend on your factoring this quadratic properly, who wants that deal? Yeah, what will you do? What are you going to do? Your entire grade depends on factoring this quadratic. What will you do? Which formula? The quadratic formula. Now, if I give you a quadratic with integer coefficients, maybe x squared minus 5x plus 6, you might be able to look at that and then just artistically see, oh, this is x minus 2, x minus 3. I see the factors. But if you don't see the factors, what do? Roll up your sleeves and you do the quadratic formula. So you can try to do it quickly by just glancing at it and seeing, can you do the algebra? But if not, you have something you can fall back on. Choosing which test to use, it's a lot like dealing with a newborn crying baby. Right? If you have a newborn crying baby, what should you do? I will risk asking this question.
What's the question?
You have a newborn crying baby, what do you do? Okay, so give me some options.
Rock the baby.
Rock the baby, good answer. Feed the baby, what else? Give it a pacifier, what else? You might be the mom, but give it to someone else. Hopefully a handoff and not a deep bomb. What else?
Make a funny face.
Make a funny face, try to entertain the baby. Thank you. I was hoping somebody would mention change the diaper. Yes, change the diaper. There's a lot of different things you can try. Eventually, you start to learn, that's the I need a new diaper. That's the I need a bottle. That's the I want to be held. And eventually you start to notice the differences. The more times you deal with the baby, the easier it is to figure out which cry it is. It's the same thing with sequences and series. We have a lot of different tests. Some tests are easier to use than others. Some tests are more successful than others. Worst case scenario, just go down the list like the crying baby. Does the ratio test work? No. Does the root test? No. Does the, yes, good. So the comparison test is actually a very easy one to use. You compare it to a sequence you understand, but you have to know which sequence to compare it to. So if you happen to choose the right thing, the comparison test is very easy to use. The ratio test, the root test, which we'll get to, are actually based on a comparison with a hidden geometric series. They're easier to use in that it's much more mechanical. But if you happen to just know what to compare it to, it's a lot faster. It's very similar to factoring a quadratic. Worst case, just use the quadratic formula. But if you are able to just quickly look at it, you might be able to do it better. So we want to find ways to tell if a sequence converges. Okay. Before we get into the different tests, One of the big things in mathematics or science, you see this in chemistry all the time, is you take complicated things and you break it into simpler ones. So if I'm trying to understand things about a complicated sum, I try to break it up into smaller pieces. So if I want to figure out the sum of an plus bn, it's related to the sum of an and the sum of bn, and so on, as long as everything is finite. So assume all sums are finite. Okay. So we are going to develop tests, but when we're applying the tests, rather than applying it to the original thing we're given, maybe we just break things up first. Just like when you did integration, if you had a lot of terms, you might just break it up and integrate term by term by term. If you have infinitely many terms, you can't necessarily do this. But as long as you only have a finite sum, a sum of 2 terms, a sum of 3 terms, a sum of 4 terms, you can do stuff like this. All right. So just to be explicit, we've had this a couple of times. The geometric series is the most important series to know. And you can use either X, you can use R. We have a formula for the finite sum. We have a formula for the limit. I reviewed that earlier today. We did that as the basketball lecture on Friday. It is amazing how many things can be done by this. Okay, so the nth term divergence test. If an does not go to 0, then the sum diverges. Does everyone agree that this is one of the of course theorems? If I'm converging, as I add more and more terms, I should be stable. I shouldn't be moving that much. If an is not going to 0, so if an is not going to 0, then there is an epsilon such that there are infinitely many n with an greater than epsilon. Because it's not going to 0, so no matter what epsilon you give me, since it's not going to 0, there must be some epsilon, some sufficiently small number such that infinitely often I'm greater than that. It doesn't mean that every epsilon you give me, maybe, for example, maybe I take an is 1 over 1,000 plus -1 to the n over 2,000. So this is fluctuating at roughly around 1 over 1,000. The terms are not going to 0. But eventually, I will have infinitely many terms. They'll be all greater than or equal to 1 over 5,000 or 1 over 10,000. Something like that will work. But they won't be greater than 1 over 10. So there's some critical threshold such that I will have infinitely many terms greater than that. So if I'm converging, well, when I add my next term, the sum is going to move by at least that amount. So it can't converge. And just some notation. This means there exists, and this means for all. So just some notation that I'm going to eventually start shifting to. The flipped E means there exists, the upside down A means for all. This just helps us as mathematicians write things quickly. All right, the next one. This is the integral test. How many have seen the integral test in high school or Math 140? All right, so this is an extremely valuable one. Let's say an equals f of n, so I have some function. And let's say f is positive and it's decreasing and continuous, then the integral of f of x dx converges, then the sum converges. If the integral diverges, then the sum diverges. There's, of course, a related one where f is positive and increasing. And one of the great uses of this is to try to approximate a sum with an integral. Is this everybody's third calculus class? Yes? How many people have taken multiple classes in summation theory? Exactly. We don't have good formulas for most sums, but we do have a lot of times good formula integrals. So a lot of times we can actually approximate sums by integrals. And there's an entire theory, if the function is increasing, there are ways to approximate finite sums with integrals. And this is an extremely valuable thing. It's, for the most part, it's useful when we're trying to figure out if something converges. Well, if something is going to converge, then I'm not going to have the ANs increasing, because if the ANs increasing, it's clearly not going to converge. So when I want to use something like this, I'm going to typically have my terms are decreasing. And so as an example, let's consider the following. Let's take AN equals 1 over n. I need a function that when I take x equals n gives me 1 over n. Can anybody give me a suggested function? What function do you think I should take? I need a function of x such that when x equals n, I get 1 over n. 1 over x. So for the most part, it's usually replace n with x. And what goes on here is here's 1, here's 2, here's 3, here's n plus 1. And if I go like this, so here's 1, here's 1/2, here's 1/3, here's 1 over n. And now, if I look at my function f of x equals 1 over x, if you look at what I've done here, my sum is going to be a little bit larger than my function. So if I integrate from 1 to n of 1 over x dx, that's going to be less than or equal to the sum of an times, I guess I'll do am times 1. M goes from 1 to say n, because all of the boxes have width 1. I could also have my boxes go the other direction. And if I have my boxes go like this, now the area under the integral is going to be larger than the boxes, except that I missed the first box. So then I would have the integral from 1 to n of 1 over x dx plus that first box 1 would be greater than or equal to something like the sum m goes from 1 to n of am times something like that. I might be off by the last term, but this is roughly what's going on. Is now, when you look at it, you can see that in this box over here, I go up to 1/2, the function is always larger than that. In this box, I go up to 1/3, the function is always larger than that. But I missed that first box in the beginning that I have to add. And so what we get is the sum m goes from 1 to n of 1 over m is basically the integral from 1 to n of 1 over x dx. And so if the integral, this is the sandwich theorem. If the integral diverges, the sum diverges. If the integral converges, the sum converges, because we can bound one by the other. Can someone tell me what the integral of 1 over x is? What function has derivative 1 over x? ln of x. So this is equal to ln of x at 1 over n, which is just the natural log of n. Or in college now, we use log at 1 over n. So it would just be the log of n. So this tells us that the sum of the harmonic series is like the log of n. If you think about what we did last time when we were doing the harmonic series, we showed every time we double the number of terms, we add at least a factor of 1/2. And if you really think about that, that is related to this logarithmic growth. So this becomes a way to show not only that the sum of 1 over n diverges, but that we have some idea of how quickly it diverges, or better yet, maybe how slowly. So here's an example where the terms are tending to 0, but the sum diverges. So this is one of the most important sequences. So the sum of 1 over n diverges. So when you're looking for a go-to example of a series that diverges, this is one of the ones you should think of. Okay, so the direct comparison test. So assume that we have positive numbers, 0 less than equal to an less than equal to bn. If the sum of bn converges, then the sum of an converges. If the sum of an diverges, then the sum of bn diverges. So if you think about this, if bn converges and all the ans are between 0 and bn, then the sum of an has to converge as well. It's important that we have that it is greater than or equal to 0. If just had equal to bn false, let an equal -1. Well, if I take -1 and I just keep adding -1, -1, -1, -1, that's going to go to -infinity. So again, always look at the conditions. And this goes back to that analysis result we claimed earlier, that if you have a sequence that's bounded from above and is increasing, it has to converge. Well, the ans are never negative, so every time I add more terms, this sum is getting larger and larger and larger. But because the bn's are bounded, because that whole sum is bounded and converges, the sum of the an can't get above that, so I can just appeal to that previous result. So I just use that previous result here. Conversely, if that sum diverges and the bn sum is larger, well, then that diverges. What if I tell you that the sum of bn diverges? What do you know? If the sum of bn diverges, do we know anything? Nothing. All we know is the sum of an is less than or equal to infinity. Thank you. What if we know the sum of an converges? Do we know anything? Nothing. We just know that the sum of bn is at least something finite. Well, great. It's not really that big of a deal to know something is at least a finite number. It's also not that big of a deal to know that something is at most positive infinity. So when you have results like this, where are they useful? Well, this is only useful if the sum of bn is finite. If the sum of bn is infinite, it's not going to help. So this is one way to try to prove that a sum converges. If I can find a sum that I know converges, and I know term by term I'm less than or equal to, I win. I just have to find something that's less than or equal to term by term. Does it have to be every single term? What if it's every term but one? Is that okay? Is it okay if there's one term that's not less? So let's say every term of an is less than or equal to every term of bn except for term 2023, where for term 2023, the an term is just larger. Is that enough to then say, oh crap, we can't use this result? Or are we okay if one term is bad? So we can't use it the way it's stated, but what we could do is we could just remove that term from both an and bn. Just remove the term 2023, and now it holds. And I've only removed one term, so this sum is still going to converge. If things diverge, it would still diverge if I remove one term. If I remove one term, it's okay. So all I need is that this holds for all but finitely many terms. Only need for all but finitely many. I could have finitely many exceptions. I could have 2 billion exceptions and everything would be fine. I can't have infinitely many exceptions. As long as it's finitely many, just remove them, just remove them, just remove them, just remove them, because a finite sum of finite numbers is finite. Okay, so when you have results like this, it doesn't have to always be the case. Maybe the first couple of values don't work out, but then things settle down. Okay. Whoops. All right. So we've reached the point where I can give you some homework assignments. So for Wednesday, do sections 10.1, 10.2, and 10.3. So the only one I want to make sure is Has everybody here seen Lhopital's rule? Is there anybody who has not seen Lhopital's rule from Calc 2? Okay. You know you have made it in life when your name has become a verb. You Lhopital something. Okay. So for example, if I give you the limit as x goes to a of f of x over g of x, if this is 0 over 0 or infinity over infinity, this is the same as the limit as x goes to a of f prime of x over g prime of x. What if that's still 0 over 0 or infinity over infinity? What do? You do it again, right? What's better than a Lhopital problem? A double Lhopital problem. And eventually the hope is that you will stop doing Lhopitaling. That you will only have to Lhopital finitely often. So the question is, why is Lhopital true? Quick proof, Lhopital. Proof. Say we have 0 over 0. F of x over g of x. Does everyone agree that it's equal to this? Can I subtract f of a from both? Why? What does f of a equal? I'm sorry. I'll do f of a upstairs and I'll do g of a downstairs. Why can I do this? What do f of a and g of a equal? What am I assuming that f of a and g of a equal right now? 0. So I'm assuming both f of a and g of a is 0. Can I divide both by x minus a? What is 1 over x minus a divided by 1 over x minus a? That equals 1. Wow, I mean, this is a great day. We've done nothing twice. Right, it's exhausting to do this little. Now we can just take the limit as x goes to a. And now we'll have, that's going to go to f prime, that's going to go to g prime. I'll use the limit of a quotient as the quotient of the limits, which is okay so long as this is not 0. So as long as I don't have 0 over 0, again, this is a proof of Lhopital for 0 over 0. If I have 0 over 0, this is not a proof. I then have to do more work. You don't want to see it, I don't want to do it. If I'm wrong and you do want to see it, let me know. I'm happy to talk to you. I'm trying to just do enough so that you can see, why is this true? Why does Lhopital work? Well, the reason it works is I can rewrite the top in a more illuminating manner. And if I write it like this, I now have a beautiful result where I haven't changed the numerator, I haven't changed the denominator, but now as I take the limit, this is going to look really good. Okay, and it's a better way of viewing what's going on. So your homework for the next time is to look at these problems from sections 10.1, 10.2, 10.3. There'll be another 3 sections of problems coming up for Friday. Please, please, please write your name on your homework. Write Math 150 on your homework. Write the homework assignment number. Write the date it is due. Make it very easy for people. These are good life habits to get into. It is amazing how many times people send in something called CV or resume.pdf or paper.pdf. Those are deleted by a lot of companies because when people save them to the hard drive, if it's saved like that, I have gotten applications where people don't put their name anywhere. Well, it was in the email. Well, that's fine, but we download the emails and we put them all in something like this, and now I have no idea whose thing I'm reading, so gone. Really want you to get into good habits. Make it easy for people to figure out who you are. Have your homework neat, stapled. Okay, you should have a staple or paper clip on you at all times. If necessary, you can always do a staple transplant from one piece of homework to another. You remove the staple and insert into the next one. All right. Sometimes classrooms have staplers, sometimes they don't. This one doesn't. If you work with people, just write that you worked with people on the homework. I strongly encourage you to work with people. I did that all through college. Make it easy to figure out which homework problems you're doing. Clearly write down which problems you are. Do the problems in order. Make it as easy as possible for the graders. Make it clear what your answer is. I don't want to do a Where's Waldo trying to find where is your homework solution for this problem, especially on an exam. Okay, so if you have any questions, let me know, let the TAs know, let the MSRC people know. This is a good place to stop for today.